we have been looking at the notion of diagonalizability of a matrix A in R n cross n. That is, we have looked at a matrix A which is n by n and all its entries are real. We are looking at the notion of the diagonalizability of that matrix. We found the crucial thing for answering this question is the notion of eigenpairs. When we say eigenpair lambda phi, lambda is a real number and phi is a vector which has n components, such that a phi equal to lambda phi. Then we say lambda phi is an eigenpair. Lambda is called eigenvalue, sometimes called characteristic value also, and phi is called eigenvector corresponding to lambda. And here the phi we always want it to be non-zero, because otherwise this equation a phi equal to lambda phi will have solution 0 solution for any lambda. So, we are looking for those lambdas for which there is non-zero solution. Such a pair will be called an eigenpair. For diagonalizability, of A, what we found was that we need n eigenpairs. If A is an n by n matrix, in order to diagonalize A, we need n eigenpairs lambda 1 phi 1, lambda 2 phi 2 and so on lambda n phi n, such that phi 1 phi 2 phi n are linearly independent. The eigenvectors appearing in the eigenpair combination be linearly independent. Note, lambda 1, lambda 2, lambda n need not be distinct. What we mean is that some of them could be repeated. So, for diagonalizability, our problem is to find such n eigenpairs where the eigenvectors involved in the eigenpairs are linearly independent. Let us look at some simple examples. Let us take the matrix A 1 minus 3 3 minus 2 0 2 1 minus 1 3. It is a matrix which is all real entries and it is a 3 by 3 matrix. Let us consider the number lambda 1 equal to 4 and the vector phi 1 to be 1 0 1. We now verify that A phi 1 is 1 minus 3 3 minus 2 0 2 1 minus 1 3 into 1 0 1, and when we multiply we get 4 0 4, which is 4 times phi 1. Thus, we find that phi 1 is an eigenvector corresponding to eigenvalue lambda 1 equal to 4. Since lambda 1 equal to 4 is an eigenvalue and phi 1 is an eigenvector corresponding to this, we get lambda 1 phi 1, that is the number 4 and the vector 1 0 1 is an eigenpair for the matrix A. Similarly, we can verify by simple multiplication that if lambda 1 equal lambda 2 equal to 2 and phi 2 equal to 0 1 1, then A phi 2 is 2 phi 2, that is lambda 2 phi 2, and therefore, 2 and phi 2, that is 2 and the vector 0 1 1 is an eigenpair for A. Similarly, we can also verify one more eigenpair, lambda 3 equal to minus 2, phi 3 is equal to 1 1 0, satisfy A phi 3 equal to 2 phi 3, that is lambda 3 phi 3, and therefore, lambda 3 phi 3, that is minus 2 1 1 0 is also an eigenpair for A. So, therefore, we have found now we have 3 eigenpairs. What were they? Lambda 1 phi 1, where lambda 1 was 4 and phi 1 was 1 0 1, lambda 2 phi 2, where lambda 2 was 2 and phi 2 was 0 1 1, lambda 3 phi 3, where lambda 3 was minus 2 and phi 3 was 0 1 1 are eigenpairs for A, and phi 1 which was 1 0 1, phi 2 which was 0 1 1, phi 3 which was 1 1 0 are clearly linearly independent. And therefore, we have 3 eigenpairs in which the eigenvectors involved are all linearly independent, and this was our search for A to be diagonalizable. Since A has 3 eigenpairs, lambda 1 phi 1, lambda 2 phi 2, lambda 3 phi 3, where the phi 1, phi 2, phi 3 are linearly independent, and A is a 3 by 3 matrix, and we have got 3 eigenpairs, and the eigenvectors in the eigenpairs are all linearly independent. We have A is diagonalizable over R. Everything involved is over the real numbers, and so it is diagonalizable over R. What is the diagonalization process? We construct the matrix P as the matrix whose columns are these vectors phi 1, phi 2, phi 3. What does that mean? Phi 1 is 1 0 1, phi 2 is 0 1 1, and then phi 3 is 1 1 0. If we take this matrix, then P is invertible and P inverse A P will be, the first column corresponds to the eigenvalue 4, the second column corresponds to the eigenvalue 2, and the third column of P corresponds to the eigenvalue minus 2. So, these eigenvalues will come in the diagonal and all other entries will be 0, P inverse A P. Now, with this matrix P, one can easily calculate P inverse and verify indeed that P inverse A P is this diagonal matrix. So, if we have an n by n matrix where we can find n linearly independent eigenvectors and the n scalars lambda 1, lambda 2, lambda n, and thus n eigenpairs in which the eigenvectors involved are all linearly independent, then we can assert that the matrix A is diagonalizable. Let us look at another example. We note that in the previous example, in the eigenpairs that we got, the 3 numbers lambda 1, lambda 2, lambda 3, they were all distinct, but this is not necessary. These numbers may be repeated. Let us look at another example A equal to 3 minus 1 1 minus 1 3 1 0 0 4. Now, if we take lambda 1 equal to 4 and phi 1 equal to 1 0 1, we can easily verify that A phi 1 is lambda 1 phi 1. Just multiply the matrix A with this vector, you will get 4 times phi 1. Similarly, if we take lambda 2 also as 4 and phi 2 as 0 1 1, we can verify A phi 2 is again 4 phi 2, which is now lambda 2 phi 2. And finally, if we take lambda 3 equal to 2 and phi 3 is equal to 1 1 0, we can verify with that matrix A multiplying phi 3 gives us exactly 2 phi 3, which is lambda 3 phi 3. And therefore, we have 3 eigenpairs now. The first one is lambda 1 phi 1, which is 4 and 1 0 1. The second one is lambda 2 phi 2, which is 4 0 1 1, and the third one is lambda 3 phi 3 1 1 0. Notice that the number 4 repeats in the first and the second pair, but the corresponding eigenvectors we are chosen are different, and 1 0 1 the eigenvectors involved in this are linearly independent. Therefore, A is diagonalizable. A is diagonalizable. We have got for a 3 by 3 matrix A, we have found 3 eigenpairs lambda 1 phi 1, lambda 2 phi 2, lambda 3 phi 3, and the phi 1 phi 2 phi 3 are linearly independent, and hence we have A is diagonalizable. What is the diagonalizing matrix? Again we construct P, which is the matrix consisting these 3 eigenvectors along the diagonal. Then as before, P is invertible, it can be easily verified, and we can verify that P inverse A P must be a diagonal matrix. Now, what are the diagonal entries? The first column corresponds to the eigenvalue 4, the second column also corresponds to the eigenvalue 4, and the third column of P corresponds to the eigenvalue 2. So, the diagonal matrix we get will be 4 4 2 along the diagonal and all the rest 0. So, thus we see that whenever for an n by n matrix or n cross n matrix, we are able to get n eigenpairs lambda 1 phi 1, lambda 2 phi 2, lambda n phi n, where lambda 1, lambda 2, lambda n are real numbers, not necessarily distinct as we found in the last example, and the vectors phi 1, phi 2, phi n are linearly independent, then we can diagonalize the matrix. So, again we summarize this. This is the important thing to note is that if A belongs to R n n, has n eigenpairs lambda j phi j, j running from 1 to n. So, if it has n eigenpairs where phi 1, phi 2 are linearly independent, then of course, these vectors phi 1, phi 2 are in R n, they are all real vectors, then A is diagonalizable. And how do we diagonalize it? If we set the matrix P to be the matrix whose columns are these phi 1, phi 2, phi n, then P inverse exists and P inverse A P will be the diagonal matrix which will have this lambda 1, lambda 2, lambda n along the diagonal entries. Therefore, the model of the story is, in order that you decide or you want to diagonalize a matrix, whether you want to decide whether a matrix is diagonalizable or not, and when you have decided that it is diagonalizable, how do you diagonalize it? What is the matrix P that makes P inverse A P diagonal? All these depend on finding these eigenpairs. If there are n eigenpairs, we are done. We know it is diagonalizable, we can construct the matrix P with the columns as this n diagonal. So, our search therefore is for these eigenvalues and eigenvectors. Thus, the diagonalization question crucially depends, actually the answer to the diagonalization question, crucially depends on finding these eigenpairs. Crucially depends on finding these eigenpairs. Not only we want to find the eigenpairs, we want to find n of them, we want to find the n of them in such a way that the numbers lambda 1, lambda 2, lambda n are real and the vectors phi 1, phi 2, phi n are linearly independent. So, the question that arises, where do we look for these eigenpairs? Where do we look for these eigenpairs? That should be our main goal. In fact, this is going to occupy the main analysis of diagonalizability or otherwise of a given matrix, the search for these eigenpairs. So, we shall now begin our analysis to find the answer to this question of where do we look for these eigenpairs. So, looking for eigenpairs involves several things. We want to look for those numbers lambda 1, lambda 2, lambda n. We want these numbers to be real numbers, and then we have to look for those vectors phi 1, phi 2, phi n, and we want them to be linearly independent and a phi j to be equal to lambda j phi j. So, these are the ingredients that we are looking for in the numbers and the scalars that we are hunting for. Okay. So, in order to hunt for these numbers and scalars, we must know something about them. We should know how they look like, so that we can go and grab and see, are you the one who are going to satisfy me. So, what we want to do is, let us look at the eigenvalues, that is these numbers are called the numbers appearing in the eigenpairs are the eigenvalues. So, we will look at some analysis of the eigenvalues to familiarize ourselves as to how an eigenvalue should look like or where we should go and look for. Remember, we are looking for the eigenvalue as a real number. So, we have to look for this eigenvalue in this world of real numbers, which is infinite. So, we are going to search for n needles in an infinite stack of needles. So, it is very difficult to identify these fellows. So, we must have some way of identifying the particular needle, the particular number that we are going to look for. So, therefore, we are going to analyze. So, suppose we have a matrix A which is n cross n real matrix, and lambda, a real number, is an eigenvalue of A. Suppose, so we catch hold of one of the known friends of A, namely the eigenvalues, and start analyzing him and see how he looks like. Now, because he is an eigenvalue, every eigenvalue has an eigenvector. When is so therefore, this means, so suppose A is an n by n real matrix and lambda a real number is an eigenvalue of A, then this implies there exists a vector u which is not 0 vector such that A u equal to lambda u. This is the requirement of an eigenvalue. An eigenvalue should always have an eigenpair or a vector u such that A u equal to lambda u. If that is the case, this says lambda I minus A u equal to theta n, and remember u is non-zero. So, there is a vector u non-zero such that lambda I minus A u equal to theta n. Now, what does that tell us? Now, let us call this matrix lambda I minus A for the time being as A sub lambda. So, there exists, if lambda were an eigenvalue of A, then there may exist an vector u which is different from 0 such that A lambda u equal to theta n. This says the system A lambda x equal to theta n has a non-trivial solution u. Has a non-trivial solution u. Now, A lambda is, since A is real, lambda is real, I is real, A lambda is also a real n by n matrix. So, this is a system, this is a homogeneous system, this is a homogeneous system whose matrix is A lambda. So, this homogeneous system corresponding to the matrix A lambda has a non-trivial solution u. This immediately tells us that A lambda is not invertible, because if A lambda were invertible, this system will have x is equal to A lambda inverse theta, which is 0. So, x will be 0, but we have a non-trivial solution u. Therefore, in order that the system has a non-trivial solution, A lambda must be not invertible. If it were not invertible, that means the determinant of A lambda must be equal to 0, because we know that a matrix is invertible if the determinant is not 0. So, not invertible, therefore, the determinant must be equal to 0. So, let us write it. A lambda was determinant, lambda was A lambda was defined to be lambda I minus A. So, what is the conclusion that we have got? The conclusion is that if lambda belonging to R is an eigenvalue of A, of course, A is a n by n matrix and real, A is an eigenvalue of A, lambda is an eigenvalue of A, implies determinant of lambda I minus A must be equal to 0. This is our conclusion of the above discussion. Let us go through this argument again. We said that suppose A is a n by n matrix, then if lambda is an eigenvalue, there is an u such that u is not 0 and A u is lambda u. This implies lambda I minus u equal to theta n. This implies A lambda u equal to theta n, where A lambda was the matrix lambda I minus A. Therefore, the system A lambda x equal to theta n has non-trivial solution u. Therefore, the determinant A lambda is not invertible. Therefore, the determinant is 0, and hence we get that if lambda is an eigenvalue of A, then determinant of lambda I minus A equal to 0. So, we know some property of an eigenvalue of A. If something has to be an eigenvalue of A, minimum it should be such that the determinant of lambda I minus A is 0. Conversely, suppose determinant of lambda I minus a equal to 0. Determinant of lambda I minus a equal to 0 implies now the matrix lambda I minus a is not invertible, because the moment the determinant is 0, the matrix cannot be invertible. If this is not invertible, that means the system lambda I minus a x equal to theta n, the homogeneous system, must have a non-trivial solution u belonging to R n. When I say non-trivial, I mean u not equal to theta n. This means a x equal to a u. This means a u equal to lambda u, that says lambda is an eigenvalue with eigenvector u. So, therefore, what we have is that this is the conclusion 2 we have got, is that determinant lambda belonging to R, determinant of lambda I minus a equal to 0 implies lambda is an eigenvalue of a. Now, comparing conclusion 1 and conclusion 2, we see that each is the converse of the other, and therefore, combining these two we get the important result or theorem, whatever we want to call it, namely that A belongs to R n cross n, A is a real n by n matrix, lambda belongs to R, then lambda eigenvalue of A if and only if, because we have seen both ways it is true, determinant of lambda I minus a equal to 0. So, now we have got a characterization of the eigenvalues of A. What is the characterization? It has to make the determinant of lambda I minus a equal to 0. So, we do not have to search all over the place for this eigenvalue. In this infinite world of real numbers, we have to look for those fellows who make the determinant 0. Okay. This particular determinant determinant of lambda I minus a 0. So, therefore, we must look for the eigenvalues as the roots of the function determinant lambda I minus a equal to. We have to find it as the roots of this function. So, now we know, given the matrix A, how do you go about searching for the eigenvalues? First, you construct this function, which is now a function of, we will call it d lambda. This is a function of lambda. Whichever point at which this function becomes 0, that is going to be an eigenvalue. If 4 is a point such that d 4, that is determinant of 4 I minus a, is equal to 0, then automatically 4 must be an eigenvalue. So, every root of this function d lambda must be equal to must be an eigenvalue of a. So, therefore, the search now we know is going to depend on the zeros or the roots of this function d lambda. Now, we have some control of our search for the eigenvalues, and therefore, we must analyze this function d lambda in order to understand better about its zeros, because the zeros are going to be our eigenvalues. So, let us analyze. So, the search depends When I say the search for eigenvalues. The search for eigenvalues depends on our analysis of this function d lambda equal to determinant of lambda I minus a. So, we will now look at this function. So, now determinant of lambda I minus a looks like, see, the lambda I is only the identity matrix with the lambda stuck along the diagonals. So, it is a diagonal matrix with the lambda stuck along the diagonals, and from that we have to subtract the matrix A. So, we get the determinant as lambda minus a 1 1 minus a 1 2 minus a 1 m. It is simply the matrix minus A, except that along the diagonals we have to stick lambda. So, it is minus a to 1 lambda minus a to 2 minus a to n, and so on. The last will be minus a n 1 minus a n 2 and then lambda minus a n. So, this is the n by n determinant, which is determinant of lambda I minus a. When we expand this determinant, we see that the product of the diagonal terms is one of the terms in the expansion will give lambda to the power of n. That is the highest power of lambda we can get, and thus it is going to be first there is going to be a lambda to the power of n term, and since every entry is either a linear polynomial lambda or a constant, and the determinant is simply the product involves the product of the entries, the determinant is going to be simply product of some of these polynomials, and hence it is going to be a polynomial. And we have seen that the highest degree term is lambda to the power of n. So, this is one a polynomial in lambda. 2, it is a polynomial with real coefficients, because every entry is real there. So, all the coefficients are going to be real in that polynomial, and since the highest degree term of degree n, highest degree term is going to be lambda to the n. So, degree n, and the highest degree term lambda to the power of n has coefficient 1, because it involves the product of the lambda, lambda and lambda, which is along the diagonal. So, with leading coefficient, when I say leading coefficient, I mean the coefficient of the highest degree term, the leading coefficient as 1. So, we have the 4 important properties of the eigenvalues of the determinant of lambda I minus a. It is a polynomial, it is a polynomial with real coefficients, it is a polynomial with real coefficients of degree n, it is a polynomial of real coefficients with degree n, and leading coefficient is 1. Whenever the leading coefficient is 1, we call it a monic polynomial. So, thus this d lambda is a monic polynomial of degree n with real coefficients. This is called the characteristic polynomial of the matrix A. So, this polynomial is called the characteristic polynomial of the matrix A, and denoted by, say let us say C A lambda. So, the C A lambda is, by our observations above, is a monic polynomial of degree n with real coefficients. when A is a real matrix, we are considering real matrix. So, when A is a real matrix, the characteristic polynomial of A is a monic polynomial of degree n with real coefficients. So, as we are interested in the zeros or the roots of these polynomials, because we have seen that the zeros or the roots of this function d lambda are the eigenvalues. Now, d lambda is what now our CA lambda is, it is a polynomial, and therefore, the eigenvalues of A are the roots of this polynomial. So, when we are looking for eigenvalues of A, when we are working with the real numbers, we are looking for real eigenvalues, and therefore, we are looking for the real roots. Whenever we are working over the real numbers, we have to work only for with real roots. So, when we are working of diagonalization problem with the real numbers, then we are looking for real eigenvalues, and therefore, we are looking at the real roots of this polynomial. So, we are trying to solve this equation and find the values solutions of this. So, this equation is called the characteristic equation of A. The equation C A lambda is called the characteristic equation of A, and we are interested in the roots or the solutions of the characteristic equation, because these are the eigenvalues of the matrix A. So, now we know exactly, see our search for the eigenvalues has now come down to finding the roots of a polynomial. You do not have to go around searching all over the real numbers. Given the matrix A, we construct this determinant lambda I minus A. When we expand it, we get a polynomial, and this polynomial C A lambda is a polynomial of degree n. It has real coefficients, monic. So, we have a polynomial of degree n. The moment we find the roots of this polynomial, our search for the eigenvalues is over, because they are lying there. Every eigenvalue is in the roots, and every root is an eigenvalue. So, our search for the eigenvalues therefore, simply boils down to finding the real roots of the polynomial C A lambda. Now, if you look at a simple example, one of our earlier examples, if you take the matrix A 1 minus 3 3 minus 2 0 2 1 minus 1 3, then what is C A lambda? It is the determinant of lambda I minus A. So, what is the determinant? It is lambda minus 1 3. We have to negate A and stick lambda along the diagonal. Negate A and stick lambda along this determinant, and when we expand this determinant turns out to be lambda minus 4 into lambda minus 2 into lambda plus 2. Therefore, the roots are lambda 1 equal to 4, lambda 2 equal to 2, and lambda 3 equal to minus 2. You may recall the earlier example we saw when we looked at examples of eigenpairs. In the first example, these were the 3 numbers that appeared in the 3 eigenpairs. The first eigenpair had 4, the second eigenpair had 2, and the last eigenpair had minus 2. So, these eigenvalues will obviously occur in this eigenpair combination. So, here is a matrix A. When we write the characteristic polynomial, we get, remember when you expand this, you will get lambda cubed is the first term. So, it is a polynomial of degree 3. So, this is polynomial of degree 3, and since the highest term is lambda cube, it is a monic polynomial of degree 3, and everything involved is real number. So, it is real coefficients. So, the characteristic polynomial is a monic polynomial of degree 3 with real coefficient. The degree is 3 because we are dealing with a 3 by 3 matrix. If we deal with an n by n matrix, our degree will be n. So, therefore, the roots of this characteristic polynomial, namely 4, 2 and minus 2 are the eigenvalues of this matrix. Let us look at another example. This is again the same matrix which we considered earlier to give example for eigenpairs. Suppose we consider this matrix. What is the characteristic polynomial C A lambda? That is determinant of lambda I minus A. Now, if I write lambda I minus A, I have to negate A and then stick a lambda along the diagonal, that is the determinant. Write the negative of A and stick a lambda along the diagonal. If we expand this determinant, this turns out to be lambda minus 4 whole squared into lambda minus 2. So, this again is a monic polynomial of degree 3. The degree is 3 because it is a 3 by 3 matrix, and when you expand this there will be a lambda squared term here in this first and lambda term in the second, the product will be lambda cubed. So, this monic, the cube term has coefficient 1. So, it is a monic polynomial of degree 3, and since everything involved coefficients are real, is with real coefficients. So, a 3 by 3 matrix monic polynomial of degree 3 with real coefficients. What are the roots? In this case, there are only 2 roots actually, one of them is repeated. So, lambda 1 equal to 4 repeated twice and lambda 2 equal to 2. So, really speaking there are only 2 eigenvalues 4 and 2, but one of them is repeated twice. So, these are the eigenvalues. These are the eigenvalues of E. So, therefore, we must remember if we are dealing with real matrices and we are dealing with real diagonalizability, then we are looking for real eigenvalues. Let us look at another simple example. Let us consider the matrix A, which is 0, minus 1, 1, 0. This is again a real matrix 2 by 2. So, its characteristic polynomial now must be a monic polynomial of degree 2 because it is a 2 by 2 matrix. So, let us write the characteristic polynomial, which is negate the matrix and then you have to stick a lambda along the diagonal. So, it is going to be lambda along the diagonal, and when you expand this you get lambda squared plus 1. Now, what are the eigenvalues? If you are working in R, we are looking for real roots of C A lambda, but lambda squared plus 1 equal to 0 has no real roots. So, has no real roots. Therefore, no real eigenvalues. The moment you do not have any eigenvalues, therefore, no eigenpairs. The moment you do not have eigenpair, there is no diagonalizability over R, because we are looking at R. So, this example is a striking example in the sense that if you are dealing with real matrices and if you want to do real diagonalizability, it is not always possible, because here is a matrix which is real, it is simple 2 by 2 and it has no real eigenvalues and therefore, there is no possibility of real diagonalizability. Why did this happen? So, therefore, even though the matrix, the above matrix is real, it does not have any real eigenvalues. So, what is the problem? Why did this happen? This happens because we are looking for the eigenvalues as the roots of the characteristic polynomial. The characteristic polynomial is a polynomial of degree n with real coefficients, but in general a polynomial of degree n with real coefficients may not have real roots, and if it has real roots, all of them may not be real, some of them may be real, some of them may be complex, and those who appear as complex root must appear in complex conjugate pairs. So, therefore, solving polynomial equations with real coefficients over the reals, we may not have any roots or we may not have enough number of roots. That is one of the algebraic deficiencies of the real numbers. In fact, it is in order to eliminate this algebraic deficiency of real numbers, the complex numbers have been created. So, let us note that this problem arises, this difficulty arises since we are seeking eigenvalues for A belonging to R n cross n as roots of a real polynomial, or let us say a polynomial with real coefficients, a polynomial with real coefficients, but in general a polynomial of degree n with real coefficients one may not have real roots or if it has real roots, it may not have n real roots. So, therefore, there is already a big stumbling block in our search for eigenvalues if you are working in the realm of real numbers. This is because of the algebraic deficiency of the real numbers. What is said as the real numbers are not algebraically closed, that is polynomials with real coefficients cannot be factorized completely over the real numbers, that is they may not have real roots. Hence, there are irreducible polynomials with real coefficients of degree more than 1. Therefore, we are stuck here. Now, as a first step, instead of looking at the problem as to what is the alternative that is available, we will overcome this difficulty by saying that okay, we will allow complex roots also, because in the above the above example suggested there is going to be problem. If we had allowed complex eigenvalues also, which means we allow the eigenpairs to be complex pairs, where the number lambda can be complex and the vector phi can be complex even though the matrix is real, then for example, lambda squared plus 1 will have roots plus or minus I. Therefore, we will have 2 eigenvalues. Hence, as a first corrective step, we will say even if the matrix is real, we will allow complex roots of the characteristic polynomial and we will allow complex eigenvectors. which simply means that we will now expand our realm and say we treat all matrices as complex matrices. A real matrix can also be treated as a complex matrix, and therefore, we will think of everything as over CNN. And if you are lucky that we get all the roots as real, then we can work within the realm of the real numbers itself. Therefore, in order to avoid this difficulty, we shall allow complex eigenvalue. And hence, complex eigenvectors if necessary. Therefore, we look at the problem as that of diagonalizing a complex matrix over the complex numbers. That is, to find P which can be in C n cross n invertible such that P inverse A B P is D a diagonal matrix in C n n. So, therefore, we expand everything to the domain of complex numbers. Why do we do that? What is the advantage? Now, we get C A, the characteristic polynomial, as we can treat this as a polynomial monic of degree n with complex coefficients the monic polynomial of degree n with complex coefficients, and the fundamental theorem of algebra says that if you have a complex polynomial with degree n, it will have n roots. Maybe some of the roots are repeated, but if you count the repetitions, the total number of roots will be n, which means a complex polynomials can be completely factored into linear polynomials by fundamental theorem of algebra. C A lambda will have n roots, the roots may be complex, some of them may be repeated. If in particular A is real, is a real matrix, then the polynomial will be real polynomial, and therefore, the complex roots must appear in conjugate. The complex roots will appear in conjugate pairs. So, what this says is that as far as the search for the eigenvalues is concerned, there is no problem about finding them, enough number of them, in fact, n of them as the roots of the characteristic polynomial, provided you allow complex roots. Okay. Hence, we will be able to successfully we will see what is meant by successfully search for n eigenvalues of A as the n roots of the characteristic polynomial. And I assert and I repeat that these n roots could be complex also. If A is complex, the n roots can be complex, and if A is real, still the n roots can be complex, but whenever a complex root appears as a root, its conjugate pair must also appear as a conjugate. So, what is the moral? The moral is, if we allow complex roots, C A lambda can be factored. Say lambda 1 is a root, maybe it repeats A 1 times, lambda 2 is a root, maybe it repeats A 2 times, lambda k is a root, maybe it repeats A k times, lambda 1, lambda 2, lambda k distinct roots A 1, A 2, A k, their repetitions. Thus, our search for eigenvalues, we have a clear idea now as to where we should look for them. Given the matrix A, construct the characteristic polynomial, look for its roots. Now, knowing about eigenvalues, we shall now in the next lecture look at how we go and search for the eigenvectors.